Good afternoon, students. Our lecture today is about artificial neural network. It is a paradigm of machine learning which is inspired by neurosciences that deals with the human nervous system as well as the working of human brain. So artificial neural network describe a computational model that describes how human brain performs complicated calculations and learn different concepts. The list of our agenda item includes learning with multiple perceptrons as well as sigmoidal perceptron. And using sigmoidal perceptron, we are going to develop a computational model of a neuron. And then we shall focus on constructing an artificial neural network using multiple sigmoidal perceptron. Alright, so we're going to start with an example problem. We are given 4 data points and 2 of them have one label, which is this blue circle. The other 2 have a different label, which is basically this red cross. Obviously, one can see that it is difficult to split or to define a boundary using a linear classifier that can help us learn this function. So in other words, there cannot be a straight line which can separate these blue dots, blue circles from the red crosses, and therefore this cannot be learned by a single perceptron. So last time we talked about a possible solution to this problem where we were trying to learn a function which a simple perceptron or a linear classifier was unable to learn, and the concept was the support vector machine. But that begs another question, that is there any other tool that can be employed to learn these kind of functions where perceptron learning just doesn't work? So what else is there? And that's exactly what we're going to explore in our lecture today. Now, quite naturally, if we know that the single perceptron is not going to work, then one can resort to using multiple perceptron. So the idea here is that we can use 2 straight lines and somehow combine these 2 linear classifiers by using some kind of a logic, and to be able to say that the data points which lie between these 2 lines have one label, and the data points which lie outside this region, such as here and here, have a different label. So that's how you can use multiple perceptron to get the correct classification done. To be specific, we are going to define 2 lines, L1 and L2. And we're going to say that the data points which lie above L2 and below L1 have one label, which is blue circle, and these are separated from the data points which lie below L2 and above L1. And these data points have a different label, that is the red cross. And students are encouraged to calculate the coefficients of the 2 straight lines by themselves, L1 and L2. So in a sense, we have defined 2 regions. One of them is here between L1 and L2. And all the data points which belong to this region have one label, and the data points which are outside this region have a different label. And the important thing over here is this AND logic. So we know how to learn a concept using a perceptron such as L1, and we also know how to learn a concept using another perceptron L2. But a new thing over here is this AND logic. So let's see what are we going to make of this logic AND. So we wish to combine the 2 perceptrons L1 and L2 using AND logic or AND operation. And for that, it is important to define certain notation. So we're going to use this capital X to represent a data point. Now this data point can either have a label blue circle or red cross. And we know from our knowledge of straight line that if a point is lying below a straight line L1, then if you plug in that point in the equation of the straight line, the answer will be less than 0. And if a point lies above straight line, and if you plug in that data point into the equation of the straight line, the answer is greater than 0. So if we want to apply this AND logic between L1 and L2, then we're going to say that for the blue circle data points, L1 of X is less than 0 and L2 of X is greater than 0. And for the cross data points, L1X is greater than 0 and L2X is less than 0. For the case of binary classification, we have only two types of labels, and those can be thought of as the input of some function f. And so each of these labels would map to some number, 0 or 1 in this case. So in a sense, the output of the function is binary. Further, if we restrict the values of the inputs x1 and x2 to have only two values, if we restrict our inputs to have only two values, 0 and 1, then the whole sample space of the input will contain only 4 data points as shown here. So in that situation, the nature of this function is the Boolean. In a sense, we are trying to learn a Boolean function which is unknown. So this f of x is an unknown Boolean function where the inputs are Boolean and the output is also a Boolean quantity. So at this point, can you guess what Boolean function is this diagram representing? And yes, you may have guessed it correctly. Quite unsurprisingly, it is representing an exclusive OR function, or XOR. So f of x is an exclusive OR function, and it is also represented by the truth table shown here. So let us try to recall what does we mean when we say we wish to learn some function f of x. This learning basically means the classification of the data points x, where x becomes the input to the function. And we said before that we can classify these data points using two perceptrons, L1 and L2. And this classification will be perfectly correct, provided that we can combine the two perceptrons using some AND logic. And if we can do that, we can possibly learn the unknown function, which is exclusive OR. Now let us try to think about a situation in which we can use two perceptrons to learn the unknown function f. So we start with the first perceptron, which is L2, and it is shown by the straight line here. And I'm going to integrate this L2 into the truth table by deviating somewhat from the norms of the Boolean truth table that you are familiar with. So at the input side, the input is still binary, but the output is not 0 and 1. I'm going to use plus and minus, and there is a good reason for that. Because the output is a number that we obtain the moment we plug in the data point into the equation of a straight line. In this case, the straight line is L2. And so the number will either be positive or will it be negative? It can also be 0 if the point lies exactly on the straight line, but we are not considering those cases here. And quite visible from the diagram is that there is no data point that is going to fall exactly on this straight line. So anyways, so given this situation, so data point 0, 0 clearly lies below this straight line. So if you plug in that data point, you're going to get some minus quantity. But all other data points 1, 0, 0, 1 and 1, 1, they are lying above L2 and they are going to return some positive number when plugged into L2. Repeat this for the other perceptron L1. And if you develop the truth table like we did before, in this case there are 3 data points which are going to lie below L1, 0, 0, 1, 0 and 0, 1. And there's only one data point that lies above L1. So that is going to give us some positive number. Now combine the two perceptron using an AND logic. So here in the truth table, the outputs L1 of x and L2 of x have been juxtaposed. So for each data point, we're going to see the sign of the number that we get when that data point is plugged into L1 and L2. So 0, 0 is going to give us minus minus, 1, 0 minus plus, 0, 1 minus plus, and 1, 1 plus plus. Now if we want to combine the two perceptrons to give us the correct classifier, we're going to say that a point that lies below L1 and the point that lies above L2, basically we're talking about this region. So all the data points in this region are basically lying above L2 and below L1. They have one label. And the data points which are outside this region, like here or here, they have a different label. So in that sense, we're going to say that the logic goes that when L1 of x is negative, and therefore to represent this, I have put this bar over L1. So when L1 of x is negative and L2 of x is positive, it means we are talking about this region over here. And this is going to give us a correct classifier. In order to complete the AND logic, AND of L1 bar and L2, which means that L1 needs to be negative and L2 should be positive. We're going to develop that logic using another perceptron. So first of all, let's look at this truth table over here. So the input of this truth table is L1 of x and L2 of x, and it is not 0 and 1, rather we are going to use plus and minus as shown here. So the input will be plus or minus, still binary in that sense. And we are going to define a function g of y. So y is representing our new data point, which is L1, L2. And for the sake of simplicity, I'm assuming that g is just binary. You can say plus minus, or you could just say 0 and 1. So the entry of our interest is here. When L1 is negative and L2 is positive, that's where this function should have one label or one value, and the function should have a different value or a different label for all other input combinations, such as this and this. And all of that can be represented in the form of another graph shown here. So this function g has input y, which is a data point represented by blue circle and red cross. And the location of these points is somewhat arbitrary, but the quadrant is important. So you see that this blue circle lies in the second quadrant where L1 of x is negative and L2 of x is positive. Whereas the other three data points are such that when, for instance, if you look at this data point, here both L1 and L2, they are negative, and here L2 is negative, but L1 is positive, and here both are positive. So the quadrants are important in this case. So anyways, our goal here is to learn this function g of L1, L2. So in other words, we are saying that in order to learn the AND logic, L1 bar comma L2, we must be able to classify these data points shown here. And as you can see that the classification in this case will not be very difficult. We just need to draw a straight line, perhaps something like this, which can separate this blue circle from the red crosses. An example classifier is shown by the straight line here, m of y, which is a boundary between the blue circle data points and the red cross data points. But note that this is just one example classifier. You can think of other linear classifiers. For example, you can also separate the two types of data points by using this kind of a straight line, or maybe just a horizontal. And there can be many other options as well. So the important thing to learn over here is that we were able to learn this unknown function g of L1 and L2, which is basically an AND of L1 bar and L2, by using single perceptron. So in this case, we did not need two perceptron, only one was sufficient. Let us put things together and try to summarize what we have said so far. So essentially, we have two graphs. The one shown on the left is representing the input space, where the coordinates are the original data points, coordinates x1 and x2 used for the training. And we said that we could separate the blue circles from the red crosses using two perceptrons L1 and L2. In some sense, we define the space between the two perceptrons L1 and L2 to be containing the data points of one type of label, such as blue circles. And this space is different from, is separating the data points from the red crosses, which have different labels. And we have on the right hand side another plane where the space between L1 and L2 maps to the second quadrant somewhere over here on this plane. So in this plane, the coordinates are the values of the perceptrons L1 of x and L2 of x. And when we say that we want to have a point that lies above L2, which means that the value of L2 must be positive, and a point that lies below L1, which means the value of L1 should be negative. So that space maps here in this quadrant. And everything else which is outside this space maps to the third, first, and the fourth quadrant. Essentially, the classification here in this example is occurring at two different levels. At the first level, it is taking place at the input space where the data points x1, x2 have been used. But then at the next level, the classification is occurring by using the data points taken as the output of the perceptron L1 and the output of the perceptron L2. And we knew that we needed to combine L1 and L2 using some kind of an AND logic, where L1 was positive and L2 was negative. And that unknown function G in the previous slide was learned by using this state line classifier, linear classifier, which is separating this blue circle from the red cross. So in summary, L1 and L2 were the two classifiers used at first level of classification. At the next level of the classification, L1 and L2 themselves become the input of the next perceptron, which is M. Therefore, M of Y is basically representing the data points formed by L1 and L2, two coordinates. So whenever your M is 1, or sorry, whenever your M is greater than 0, it means that we are talking about this data point, which is obviously representing any data point here in this space. That data point will be classified as 1. Otherwise, the data point will be lying outside that region in the original input space, and it will be classified as 0. And this is the defining characteristic of the exclusive OR function that we wish to learn. Now, if we wish to schematically present the two-level learning of the exclusive OR function, it will be helpful to draw the signal flow diagram of this form, where the inputs are x1 and x2, and then we also have some helping inputs set to constant 1 as shown here. So you can see there are two levels at which the learning occurs, and at the first level the inputs are multiplied by the weights, x2 with a2, x1 with a1, plus a0 multiplied by constant 1. And all of them are added up to give us the perceptron L1 of x. Similarly, we have x2 multiplied by b2, x1 with b1 plus b0. They are added up to give us L2 of x. Now L1 of x and L2 of x form the input of the learning at the next level, whose output is M of y, and L1 of x will be multiplied by the coefficient C1, L2 with C2 and C0. They're all added up to give us M. And later on we shall extend this diagram to form artificial neural network building blocks. But before that, we need to fix certain things. The basic problem is that we wish to learn suitable values of these coefficients a2, a1, a0, b2, b1, b0, c2, c1, and c0, so that the network shown below can learn the unknown function, which we know is an exclusive OR function, x1, x2 in this example. However, note that one of the problems is that the output here, M of y, is not binary. It can be any number which can be positive or negative, and not just 1 and 0. So it is essentially continuous. So this is one of the problems that we need to fix before proceeding to the building block of the artificial neural network. Another problem is that output M of y has a value which may not be bounded. It can be much greater than 1 or much less than 0 or minus 1. And this is somewhat inconsistent with the data point labels, which are usually binary, 0, 1 or minus 1 and 1. This problem can be fixed easily if we could limit or saturate the value of our output to say between an interval that restricts its value between -1 and 1. And one of the things that help us to accomplish this is the sine function. So if we use a sine function defined like this, we can process our output to have a value which is either 1 or -1. Therefore, we can match the two layers with the two levels of learning. So this first layer corresponds to the computation of the two perceptrons L1 and L2 in the original data space or the input space, and the second layer corresponds to the further processing of the perceptrons L1 and L2 using a single perceptron in this particular case. And that's how we are going to describe the learning problem using two-layer network. So once we have restricted the value of the output of the network to either -1 or +1, then it is helpful to compute the error E. So error E is defined as the sine function applied to the perceptron output m of y minus y, and this y is known, it is given, it is the data label that is known to us at the time of training. So now using this error, we wish to compute the values of the coefficients. And the way we are going to do this is that we are going to take the square of the error and wish to find the minima or the minimum value of E square. And we shall see very soon that this E square actually depends on these coefficients. And therefore, we're going to differentiate E square with respect to these coefficients one by one and try to find out the minimum possible values. So our job will be to find out the values of the coefficients which minimize the error. In particular, it minimizes the error square. So once we embark on taking the derivative of the error square, we would look at the coefficients at the second layer first, which are closer to the output. So let's say we take the partial derivative of error square with respect to C1. Then one of the problems that we run into is that we need to take derivative of this sine function. And if we look at the sine function, it is discontinuous when the input of this function is 0. So it is not a differentiable function. So alternatively, we can use a similar function which is a sigmoid function, and it does not have an abrupt change or a discontinuity. This sigmoid function is defined as 1 over 1 plus e to the power minus I, where I is the input of the sigmoid function. And as you can see from the graph, that this function is relatively smooth. It is not discontinuous, therefore it is perfectly differentiable. However, note that the output of the sigmoid function is not -1 and 1, or in other words, the output is not confined between -1 and +1, rather it is confined between 0 and 1. But this is also fine as far as the binary classification is concerned. So labels -1 and 1 or 0 and 1 both will work equally fine. Time for some algebra. So let S of I be the sigmoidal function. Then it can be shown that if you take a derivative of S of I with respect to I, the input, then it satisfies a very nice property that is the derivative of S of I is a product of S of I times 1 minus S of I. So I would encourage students to prove this property as a homework exercise. As a consequence, it greatly simplifies the weight update rule. And by weight, I mean the coefficients, A's and B's and C's. Alright, so we're going to define some terms here. A dot product, C dot L. So C dot L is defined as C2 times L2 plus C1 L1 plus C naught. S applied to C dot L, 1 over 1 plus e to the power minus C dot L. And if you take a derivative S prime with respect to C dot L, this is what you're going to get. Now, if we wish to compute the partial derivative of the error square with respect to the coefficients which are closer to the output, C1, C2, and C naught, then our best friend is a chain rule. And it is because the error function is actually a function of S, whose input is C dot L. So if you take a partial derivative of E squared with respect to C1, you are going to get 2 times S C dot L minus Y multiplied by the partial derivative of S C dot L with respect to C1. And therefore, when you take a if you want to compute the partial derivative of SCL with respect to C1, you need to apply the chain rule. So S will be first differentiated with respect to the input C dot L, and then you're going to take a derivative of C dot L with respect to C1, and you're going to get S prime C dot L times L1. So therefore, the partial derivative of E squared with respect to C1 as a whole would be 2 times S C dot L minus Y times S C dot L multiplied by 1 minus S C dot L times L1. And to keep things simple, we're going to encapsulate this part of the product, and we're going to call it delta of C, where C indicates that the dot product will be taken with one of the argument being C. And it will be apparent later on that this argument is sufficient to define the dot product and to specify this term. So using this delta, we can define the weight update rule. In a sense, if we talk about a specific weight or a coefficient, C1, then C1 of the current iteration equals C1 of the previous iteration minus alpha times delta C times L1. And delta C, L1 are computed from the current iteration. And we're going to replicate this for the other coefficients C2 as well as C0. So one of the things that you may have noted is that the weight update rule is an iterative process. We are going to utilize the result of the previous iteration to update the coefficients in the current iteration, and then use the values of the current iteration, the coefficient values in the current iteration, to find out the values in the next iteration. And we're going to update the values of deltas as well as L1 and L2. Likewise, we can calculate or update the values of the other coefficients such as C2 and C0. And if you rework what we did in the previous slide, you will find out the expression for C0 and C2 like this. And the updated values of these coefficients will be further used to calculate the values of the remaining coefficients, A's and B's. And one of the important things is how we can use this delta of C to update the remaining coefficients, and this delta of C will reappear in the expressions of A's and B's update. And once again, our best friend is going to be the chain rule. So for instance, if you take a partial derivative of E2, basically this is E2 square, then if you take a partial derivative of E2 square with respect to A2, then again you have to apply the chain rule. So we'll take a partial derivative of E2 square first with respect to SCL, because E2 first depends on SC dot L. And then you differentiate SC dot L with respect to its input, which is C dot L. And then you are going to take the partial derivative of C dot L with respect to A2. And this part of the product needs further expansion. So in one sense, we are propagating the error backward. So this is the output of our artificial neural network, and we have subtracted this output from the label, from the data label, which was Y, and we are propagating this error backward to first calculate the C's coefficient, and in the next step this error will be propagated further back to compute the other coefficients, the remaining coefficients, A's and B's. So we computed the error from the output neuron and learned how to update the weights C1, C2 and C0. Now we wish to propagate this error further to the left and compute the coefficients A0, A1 and A2. And these are the weights which are multiplied by the inputs of the neurons at the first layer of learning. So this is the first layer of learning, and this is the second layer of learning. So coming back to where we left our mathematics in the previous slide, we intended to calculate the partial derivative of C dot L with respect to A2. And if you simplify this expression and open the dot product, this is what you're going to get: C1 partial derivative of S A dot X with respect to A2. And remember, L1, as also shown in the neuron in the layer 1, L1 is A dot X, so that's A1 X1 plus A2 X2 plus A0. Therefore, to simplify partial S A dot S with respect to partial A2, you again use the chain rule, and the final answer would be S A dot X 1 minus S A dot X times X2. And again, we're going to call this quantity delta of A. So in order to update the weight A2, the coefficient, in the current iteration, we are going to use the previous value of A2 minus alpha times partial E square with respect to partial A2. And this expression, now that we have solved this, part of which was shown in the previous slide and the part over here, this is what you're going to get. This is equal to partial C. This is the part that we showed in the previous slide, times C1. The C1 is the corresponding output coefficient that is multiplied with L1 times delta of A times X2. So X2 is the input, which is multiplied by A2. By following these steps, you can easily formulate the update rules for the other coefficients, such as A1 and A0. So for A1, this is A1 from the previous iteration minus alpha times C1, which is the coefficient with which L1, the output of the neuron, whose inputs are x2, x1, and x0, with coefficients, corresponding coefficients a2, a1, a0. So this C1 over here times delta C, no change, times delta A, times x1. So this is the input which is multiplied with the coefficient a1. Likewise for a0, it is a0 minus alpha C1 delta C, no change, again delta A, no change, and this time the input over here is constant 1, so we have just omitted that. And remember, delta A is basically a product of SA dot x times 1 minus SA dot x, and partial C has been defined previously and again here for the reminder. And A dot x is A2x2 plus A1x1 plus A0. C dot L is C2L2 plus C1L1 plus C0. Accordingly, we can also update the coefficient B's, which are the coefficients with which the inputs are multiplied, but it is the second neuron at layer number 1, whose output is L2 multiplied by C2. And you can work out the equations shown here and take this as a homework exercise. So B1, B2, and B0 will be updated. The expressions are very similar to those used to update A's, except that we have B's here from the previous iteration and delta B instead of delta A, where delta B is SB dot x times 1 minus SB dot x, where B dot x is basically the dot product between B and x, where that's essentially equal to B2x2 plus B1x1 plus B0. So this quantity over here. The complete neural network to learn the exclusive OR function has total of 3 neurons. 2 of them are in the first layer, which process the data point whose 2 coordinates are x1 and x2. And we have coefficient A's and B's to be computed at this level. And the output of these 2 neurons is then further processed by the third neuron, which is going to give us the desired output. And at this layer, we are going to compute the values of the coefficient C's. Now, if we formally parse the training process of the artificial neural network, we got to define 2 phases: the forward pass and the error backpropagation step. And these 2 steps are critical to train the artificial neural network. And we're going to perform these 2 steps for each data point that we are going to use to train the neural network. So for each data point X in the training set, we are going to perform the forward pass and then the error backpropagation step. Now remember that in the forward pass, we go left to right. So we are going to use the coefficient values computed in the previous iteration. So for instance, if we wish to compute the coefficients in the iteration J, then as we saw earlier, we're going to utilize the values of the coefficients, corresponding coefficients in the previous iteration. And we're going to use the value of the data point available in the current iteration. So we iterate over the data points, and suppose we are in iteration J. So we are looking at the data point J, indicated by the superscript J. And we are going to use the values of the coefficients from the previous iterations. So current data point and the previous coefficients use them to compute L1 and L2 for the current iteration. And these are the outputs available at the first layer of neurons. Now, to compute our output for the current iteration, we're going to process the current value of L1 and L2 with the previous values of the coefficient values calculated in the previous iteration, and we're going to get the output. So the forward pass is a process of a relatively simpler computation based upon some past values of the coefficients and the current data value. And we're going to get the current output. We're going to say this is output superscript J. Now, once the forward pass is complete, we proceed to calculate the error, which is the difference between our computed output for the current iteration, that is J, and the available data label that comes with the data point, that's Y superscript J. And using this error, we are going to compute delta C for the current iteration. So the expression is the same as before, except that we have to be careful about what exactly do we mean by the SC.L for the current iteration. So this is defined here. So remember, SC.L for the current iteration is the sigmoidal function applied to the input, which is the sum of C2 previous iteration multiplied by L2 current iteration plus C1 previous iteration times L1 current iteration plus C0 J minus 1, which is the previous iteration. So we now update the values of the coefficients C1, C2 and C0 for the current iteration. So this is shown here. So C0 from the previous iteration J minus 1 minus alpha times delta C superscript J, and we have just described how to compute this quantity. So delta C of J will be again used in the C1 update as well as C2 update, and L1 superscript J and L2 superscript J, that was not described in the previous slide, so that's indicated here. That's basically, so if we talk about L1 superscript J, that's the sigmoidal function applied to A2 of the previous iteration multiplied by X2 of the current iteration plus A1 of the previous iteration multiplied by X1 of the current iteration plus A0 of the previous iteration. Similarly, you can see the definition of L2 of J as well. Continuing the error backpropagation, once the C has been updated, we go back, and now it is time to update coefficient A's as well as coefficient B's. So for these two, we are going to compute delta A of J and delta B of J, and the other knowns such as delta C of J that we showed how to compute in the previous slides. So the delta A of J and delta B of J will be computed, and the definitions are shown here, using SA.X, SB.X for the current iteration. So basically we are again using the coefficient values computed in the previous iteration and multiplying them with the current data values. So for instance, SB.X is sigmoidal function applied to B2 from the previous iteration multiplied by X2 from the current iteration plus B1 from the previous iteration multiplied by X1 of the current iteration plus B0 from the previous iteration. So once we know delta B and delta A, we next show how to update A's and B's coefficients. So here it is. A1 of the current iteration, A2 and A0. Likewise, B0 of the current iteration. Maybe I should have indicated the iteration number in the superscript. So this is B0, B1 and B2 of the current iterations, and their expressions are shown. And note that their update include not just delta A and delta B, but also delta C. And for A's update we have C1 over here, and for B updates we have C2. And this is quite natural because the neuron whose input are multiplied by the coefficient B's have the output, which is then multiplied with C2, and the neuron whose input are multiplied by the coefficient A's gives you an output which is multiplied by C1. So in a way, these weight updates make an intuitive sense as well. So in our lecture we discussed an example of neural network learning an exclusive OR function, and that utilize only three neurons. Two of them belong to the input layer and the other one to the output layer. So essentially, in terms of layers, you can see that we have two distinct layers, the input layer and the output layer, and this is still a relatively simpler artificial neural network example. In general, neural networks can be very complex, especially if we have some hidden layers that lie between the input layer and the output layer of the neurons. And if we increase the number of hidden layers, it increases our capacity to learn more and more complicated functions. Therefore, as we try to learn more and more difficult concepts using supervised machine learning paradigm that utilizes neural network, then we may wish to include the number of hidden layers. So in the case of exclusive OR function, we did not require any hidden layer, but for many practical examples, we wish to include at least one or two hidden layers, and that is very common. A buzzword nowadays, the deep neural networks or deep learning, they often call it. When the number of hidden layers is 3 or more, then the resulting artificial neural network is also known as the deep neural network, and it is an active area of research. So remember, the depth is determined not by the number of neurons, but is actually determined by the number of hidden layers. So in this example, they're showing that there are 4 hidden layers. So that's an example of a deep neural network. As a homework exercise, you will be required to design an artificial neural network that can learn a parity function f, whose input is a 3-bit number. So you can have 3 input variables x, y, and z, such that the output is 1 when we have odd number of inputs set to 1, and the function outputs 0 in case of even number of inputs when set to 1. And this will be a bit more complex than the example that we have discussed in the lecture. Try to write an expression of how you are going to update the weights or the coefficients for the neural network using backpropagation method. Alright, so this is where I would like to conclude my lecture. The textbook material and the other resources will be discussed during the Q&A section, and you are encouraged to go through the reference material to have a deeper and more elaborative understanding of the artificial neural network. So we are now going to conclude our lecture. I hope students are adequately familiarized with the artificial neural network. Obviously, it takes a bit of time as well as a lot of practice to really have an in-depth understanding. So if you have questions, please feel free to write me an email, and we can always discuss your queries and problems in the Q&A session that will be held on coming Thursday afternoon at 3 p.m. So have a good day, and I'll see you in the Q&A session on Thursday. Thank you very much. So now we're going to describe how to update the weights A2, A1 and A0. And what we did in the previous step was that we looked at the neuron model, which was giving us the output. And the input to that neuron was L1, L2, and the third input was actually a constant. We just say that L0 equals to 1, constant. But now we think about, where did this L1 come from? Well, L1 is an output of another neuron over here, whose inputs are x1, x2, and constant input 1. And these inputs are multiplied by the coefficients A2, A1, and A0 respectively. So therefore, let's catch up from where we left our mathematics in the previous slide. So we were looking at the computation of a partial derivative, partial C dot L with respect to A2. And if you compute this derivative, we are going to get C1 partial L1 over partial L2. And once again, we see that L1 is a function of A dot X. So therefore, here partial, let me see. So partial C1 L1 over partial A2 is equal to this quantity. And again, L is A dot X as we have defined in the neuron over here. And by the application of the chain rule, finally, the partial S A dot X turns out to be this. So therefore, the weight update rule of A2 will be A2 of current iteration comes from A2 of the previous iteration minus alpha delta A x2, where delta A is this quantity, and it comes from taking a partial derivative of S A dot X with respect to partial A. Now the question is, where did this partial C come from? So if you go back to the previous slide, this partial C was available because we